Hello and welcome to OpenRelay Screenside Chats Episode 4. This is Affiliates Program Part 2. To preface this a little bit, this has been true for a couple of weeks now, but the slides that you're looking at are built with reveal.js. They are web slides, and they are available online at slides.openrelay.xyz. This one is already posted, so if you're following along live, it's there, and if you're watching this after the fact, you can get the slides without having to listen to me talk. So, as a recap from last week we talked about the architectural overview of our affiliates program. We'll have a very quick overview of the overview in just a minute. We looked in depth at the contracts associated with the affiliates program. So that's our affiliate contract, our affiliate factory contract, and our proxy contract. And we also talked about how our affiliates program is a great case study for looking at OpenRelay in general, because it covers Solidity contracts, it covers microservices, and it covers front-end dApps, which really run the gamut of what we have built here at OpenRelay. So for an architectural overview, this was the full diagram that we had at the end of the architectural overview last week. If you want much more detail, go watch last week's video. But we start out with a developer who wants to build a dApp associated with OpenRelay. He goes to the affiliate factory contract and signs up. The affiliate factory contract creates a affiliate contract, which is assigned to the developer. The developer then takes that affiliate contract address and embeds it into his dApp. Meanwhile, the affiliate factory over here has notified OpenRelay's affiliate monitoring service that a new affiliate has been generated. So OpenRelay sticks that affiliate address into Redis, which then will acknowledge that this is a valid affiliate when a user uploads an order to OpenRelay. So once the developer creates their dApp, puts it live, markets it, all of that stuff, we have users who can come along and use that dApp to upload orders to OpenRelay. They go through our validation pipeline and eventually end up in our database. Then other users, potentially using other dApps or maybe the same dApp, can search the database for those orders and then take them and submit them to the 0x exchange contract. From there, the 0x exchange contract will fill the order, collect fees, and the fees will be paid out to the affiliate contract. Then the developer who created this dApp can collect 80% of the fees that were collected, and OpenRelay will get the other 20% of the fees that were collected. So again, that's our high-level overview of how our affiliate system works. Now we are going to take a look at how the dApp that is used for this developer to sign up with the exchange contract is implemented. So yeah, today we're looking at the dApp implementation. First, we're going to start out with a walkthrough of the affiliate dApp. So the affiliate dApp looks like this. It's a web application. You need some form of Web3 to interact with it. That could be MetaMask, it could be Spacesuit, it could be Parity, it could be Mist. But you need some injected Web3 system to interact with it. And you can see here that when you log into the landing page, it will prompt you to input a name for your affiliate, and it will be preloaded with one address, and it will take the first address out of your MetaMask account, so yeah, that's here, and you use that to populate this field, and it will assign 100 shares to that user. From there, you can assign a name to your DEX. You can add additional users. All you have to do is when you get done typing this field, hit enter, and it will give you another field that you can enter another address. And each address can be assigned their own set of shares. As we discussed last week, the shares in this case are weights. It's not a percentage, so it doesn't matter that we have 100 shares on the first person and 100 shares on the second person, and that adds up to more than 100% because these aren't percents, they're shares. Basically, if this person has 100 shares and this person has 100 shares, then they each have 50% of the total shares, so they will get 50%. Each of them will get 50% of the tokens that are going to be distributed to the affiliate. If this person had 90 shares and this person had 10 shares or 1,000 shares and 100 shares, doesn't matter. They get tokens proportional to the percentage of the shares that they hold. So once you have filled in a name and all of the addresses and shares in this section are valid, it will pop up with a submit button. When you hit the submit button, it gives you a confirmation dialog. The confirmation dialog gives you a lot of information. So first of all, it repeats the name that you typed back to you just to make sure that that is what you expected. And then it shows you the breakdown in terms of percentages of who is going to get tokens when those tokens get distributed. So here it says that OpenRelay is going to get 20% sent to this address. The first address in your list is going to get 40%. The second address in your list is also going to get 40%. Note that we list 2 decimal places here after the percentage. That is as precise as it gets. There is no, like if it were 33.33333, no, it just stops at 2 threes. Beyond that, you get a rounding error, and anything that doesn't get distributed at that point will just be left in the contract to be distributed next time. It also tells you that your affiliate contract will be a proxy for this contract. That is an Etherscan link to the code page for that contract, so you can go look at the affiliate contract and make sure, if you're interested in verifying the code for yourself, make sure that it's something that you can trust. And as it notes here, verify these parameters before proceeding, as they cannot be changed in the future. Once an affiliate DApp, or once an affiliate contract is deployed, we cannot change those parameters. The contract has no facilities for changing them. So you can always deploy a new contract, but the terms of this contract can't be changed once the contract is deployed. And if you do deploy a new contract, you will end up getting a new contract address, which means you will have to update any users who are sending fees to that address. So then we have a transaction confirmation dialog. Once somebody has submitted their transaction, MetaMask will pop up and ask them to confirm, tell them how much gas it's going to cost and that sort of stuff. Then basically they will sit on this page until that transaction gets confirmed, at which point it will take them directly to the dashboard. We do give them an Etherscan link in case they want to go look at the transaction on Etherscan and mash the F5 button, waiting for it to refresh and see that the transaction's been confirmed. But once the transaction has been confirmed, this page will refresh and take you directly to the affiliates dashboard. So the affiliates dashboard also starts with a welcome dialog. The welcome dialog tells you that this is the dashboard for this particular user. It pulls the name from the contract, from the affiliate contract. It tells you to bookmark this page, because this page is how you know that you can come back and check the balance that the affiliate contract has received and pay out the tokens that the affiliate contract has received. If you lose track of this, we don't have a good way for you to find it again. We might add something at some point in the future, but essentially any given dashboard has a unique affiliate address, so it's important that you bookmark the dashboard so that you can find your way back here. So we give them a URL to bookmark, we tell them to bookmark it now, we give them their affiliate address, and then we make them click a button telling me that they have bookmarked their dashboard. We don't actually record that anywhere, but if they've pushed it, then we assume that they've bookmarked their dashboard. And if they haven't and they lose their spot, then we get to tell them, we told you to bookmark your dashboard. Once you've clicked through that dialog, you end up on the dashboard. So from here, we give them the name of the DEX, we give them the address of the DEX, and we give them their token balances in all of the tokens that we track. We don't track all of the tokens. As of the first draft of this, we don't give any way for users to add custom tokens. We might do that at some point in the future, but we haven't yet. So right now we see that this user has 0 ZRX and 0 WETH. I'd also note that this is pointed at the Covan version of the contract. If it were pointed at the mainnet version of the contract, it would also show us their Embiggen balance. So for the sake of demonstration, I sent this address some Ether, which the affiliate contract, upon receiving the Ether, automatically converted it into wrapped Ether so that it could treat it as an ERC20 token, as the contract likes to deal with ERC20 tokens. And now we see that the user has a balance of 0.05 wrapped Ether, and they have a payout button. When you click the payout button, MetaMask will ask for a confirmation, and then it will tell you that the token payout has been submitted and give you another link to Etherscan in case you want to sit there and watch that transaction, wait to confirm. And then after that, you have your tokens. The affiliate dashboard zeroes out. It refreshes all of the token balances, and that's it. You have signed up for an affiliate, and you have paid out your token balances. Before I start moving into the DApp code, does anybody have any questions that I should cover from the walkthrough?
I've got one just to clarify this.
Go for it.
To be honest, I know the answer to this one already because we've talked about it. But what happens if somebody else who is not associated with that affiliate agreement goes to that page and clicks that button? Like if they're just a random person who picks an account out and just puts in the address.
Yeah, so the affiliate dashboards are not authenticated. They are not locked down in any way, because the information on the affiliate's dashboard is publicly available on the blockchain. There is no back-end service to the affiliate system. This is all a front-end dApp that communicates with the blockchain. All of this information is pulled from the blockchain and is available for anybody who wants it. As far as pushing the payout button, anybody can push the payout button. By pushing the payout button, you are paying for the gas to distribute tokens to the affiliate for this contract. Unless you are one of those affiliates, you get no advantage from pushing the payout button. You don't get any of the tokens for pushing the payout button. The affiliates associated with that contract get the tokens from pushing the payout button. So sure, if you wanted to go push other people's payout buttons and pay the gas to distribute their tokens, you would be welcome to. Yeah, and the implication there is also that you should not assume that your tokens will be paid out on any particular interval. They will be paid out when somebody comes and pushes the payout button. If you are an affiliate, you are welcome to come push the payout button anytime. If OpenRelay decides, hey, we could really use some money from one of these affiliate contracts, we'll go push the payout buttons and collect the tokens ourselves. And because of the way the payout button works, it pays out all of the affiliates at once. It's not just paying the tokens out to the person who's pushing the payout button. It's paying out the tokens to all of the affiliates. So it will have a zero balance of whatever tokens it just attempted to pay out. Anybody have any other questions?
Does the name that you supply the affiliate creation dashboard have to be unique?
No. No. So, yeah, the main reason we collect a name for on the affiliate creation dashboard is so that systems like zeroxtracker.com have something to call that relayer when they see that exchange address come through. So, basically, if an order gets filled through a particular affiliate, that order will have that affiliate as affiliate contract address listed as the fee recipient. So there are a number of services out there that monitor that and monitor the exchange contract and see when transactions get filled, and then they list the name of the relayer who provided that order. We want to give them an easy way to attach some name to it, but people should not put too much weight on the name there. You know, I could create a contract that said, you know, ERCDEX or something like that. There's no enforcement to actually prove that this contract is associated with that. It's just a way for people to provide some information about who this affiliate contract is associated with. Any other questions? All right, moving on. Next, we are going to start looking at the DApp code itself. This DApp is written in jQuery using a little bit of jQuery UI. It depends on injected Web3. It does not do anything with zero client. It does not try to work directly with hardware wallets, although if you want to use a ledger with our affiliate sign-up DApp, you can use Spacesuit, which is a Chrome plugin that works a lot like MetaMask but interacts with your ledger instead of keeping the keys on your local system. This DApp is not terribly well structured. I guess it should say it is terribly structured. It's not terribly well structured. Anyway, the code works for its size, but this is not how I would design a larger application for something that just has a few inputs and a few pieces of information to show it works. But next week, I hope we will actually be looking at a framework that we're putting together to build front-end dApps for OpenRelay that will be a lot better structured than the code we're looking at today. So broadly speaking, there are several things that you have to do with a dApp. The first thing is to make sure that your Web3 is set up. So to do this, we have to wait for the window.onload event. That basically is the deadline by which Web3 injectors should have injected Web3. Up until that event fires, we can't be sure that we will have our Web3 object. Then we check and see if we have our Web3 object. If we don't have our Web3 object, we hide the dApp, we show the warning message that says you need Web3, and then we return and don't execute the rest of our onload method because it depends on having Web3. Finally, down here, we wrap our Web3 object. So if your Web3 injector is MetaMask and you just start using the Web3 object freely, it will yell at you that the Web3 object is deprecated and that you should be using the web3.current provider to interact with your Web3 backend. So we wrap the current provider provided by maybe MetaMask, maybe something else, in a new Web3 object, which will help ensure consistent behavior across different providers, and will also make sure that in the future, when they don't just throw log warnings that you're using deprecated services, but actually get rid of those functions, we will still be able to continue using, or this dApp won't be broken because it will be using the web3.current provider instead of, say, like web3.eth.getBalance. So this is just kind of standard dApp boilerplate. You need to check and see if you have Web3. You need to show your user a message if they don't have Web3, and then you need to wrap your Web3 current provider in something else that you want to interact with. I am still used to using Web3. There are some other things coming to the fore that also wrap your current provider that maybe provide some slightly nicer interfaces. Next, we are going to look at contract setup. So depending on what network we're on, we are going to point at a different affiliate factory address. So here, we're going to call web3.version.getNetwork, and this is our wrapped Web3 object that we were just talking about. So this is going to, the get network function is going to call our callback function, which might return an error, but I've never actually seen get network return an error, which is why I'm not handling it. Or it might return a network ID. If the network ID is 42, we're on Covan, and this is our affiliate factory address. If the network ID is 5777, then we are pointed at a Ganache service, and if you've deployed those contracts the way I usually do it, this will be your affiliate address, or sorry, your affiliate factory contract address. The next thing that we need is the ABI, which is application binary interface for this contract. The ABI basically describes how other services can interact with the contract. It tells all of the functions that it can call, what those functions return, what arguments they take. It talks about what events exist, what properties those events will have. And so in order to have a good way to interact with the affiliate factory contract, we need to provide Web3 with the affiliate factory ABI. And just to give you some idea of how big the affiliate factory ABI is, it's a really long lump of JSON. And this actually isn't a very long one in the scheme of things. There are a lot of ABIs that are way longer than that. Once you have your ABI, you can create an instance of a contract, or an object to represent that contract, by passing the ABI into web3.eth.contract. And from there, you have a couple of different options. You could deploy the contract, or in this case, since we know it's already deployed, we call at, and we pass the affiliate address. So this will give us an object that we can interact with. It will have the same properties that were described, and methods that we can call that were described in the ABI up here. And it will interact with the contract at the address that we set based on the network. Any questions so far? Okay. So the next thing we need to do is get our user accounts and do stuff with them. So here we call web3.eth.getAccounts. Again, we pass in a callback function. This is more likely than the network request to throw an error, so we do sort of handle that here. And it also passes back a list of accounts. So if we got an error, or the length of the accounts list is 0, then we're going to hide our DApp and tell the user that they need Web3. In the need Web3 object that we're displaying here, we tell the user that they need to have Web3 and that it should be unlocked. Having their MetaMask account locked, or their ledger having locked, is the main reasons that we would get an error or an account length of 0 here. So by hiding the DApp and showing the Web3, the need Web3 message, we've hopefully given the user enough information to fix their situation. If we didn't get an error and the accounts list has a length of greater than 0, then we're going to show the DApp and hide the message that says you need Web3. Then we are going to find that address input that we were looking at, basically the one that's already there on the screen. If it is empty, then we are going to fill it in with the user's first Ethereum address. So generally speaking, most Web3 providers default to the first account being the important one. I actually ran into an issue earlier today where it was painful that a dApp would not let me access anything other than the first one. And there wasn't an easy way for me to change it using Spacesuit with my ledger. But even so, because MetaMask mostly uses or only gives you one account at a time, most dApps just use the first account and don't think much of it. Once we have populated that input with the address, we run our validation step. That will make sure that the address is valid. And since we just pulled it from Get Accounts, it really should be valid in this case. But that will also mark the field appropriately so that it will show up later as a valid address. We also set a timeout to check accounts once every 1,000 milliseconds or once a second. So this is going to call back to the same function that we just called a second later. The reason we do that is that users can go into MetaMask and they can change what account they're logged in with. If they have done that, we are going to want to know that they are using a different account than they used to be. You would note here, though, once we have filled in the address input once, if they change accounts, that's not going to change. It's going to stay with the same value that it had before. Another thing that I meant to mention when I was looking at the sign up page a bit earlier is when you sign up for an affiliate contract, it doesn't necessarily have to be the case that the Ethereum address submitting the sign-up transaction is one of the recipients of that affiliate contract. So if you wanted to create an affiliate contract that paid out, an address that was on a paper wallet, and you don't want to have sent any transactions from that wallet, you could create an affiliate contract where that wallet is the only recipient, and you don't have to send that transaction from that wallet. So yeah, within this service, users are free to go fill in that first address input with whatever they like. But if it's empty when we check accounts, it will fill it in with the first Web3 account. Next is the confirmation screen. I should also mention here, I am not showing you everything to do with this dApp. There are a whole bunch of things that we do in this dApp that are just there to, put a certain piece of information into the right place so it shows up for the user, or do some basic calculations. I'm not showing you all that. I'm showing you the stuff that is pertinent to interacting with Web3 and with a contract. So in this case, we have a function also not featured here called call promise. So this is going to make a call to the affiliate contract through the Web3 provider, getting the beneficiary stake attribute from the contract. And it's going to return that as a promise. So we're going to get the beneficiary stake, the sender stake, the beneficiary, and the target. All of those are going to be turned into one big promise that will resolve once all of them have completed successfully. Once that happens, this will fire, and then we pull the beneficiary stake out of slot 0, the sender stake out of slot 1, the beneficiary into slot 2, and the target into slot 3. This is how we populate the confirmation screen, which provides things like the target address and the beneficiary address, and then it has to calculate the percentages based on the beneficiary stake and the sender stake, as well as the other information the user has filled in. Then we get to the sign up submission form, and this is a longer function. But basically, when you click confirm that you want to sign up for an affiliate contract, it's going to close the dialog that you were looking at. then it's going to create a list of stakeholders and a list of stakes. These are some of the arguments that we have to pass into the affiliate contract sign-up function. So to generate those, it's going to iterate all over all of the table rows with the affiliate row class that also have the valid address class. Now, we didn't show the submit button if they had any invalid addresses at all. So they should not be submitting anything that has malformed address. But we're going to find all of the rows with valid addresses, and then we are going to take the address and push it onto the stakeholders list, and we are going to take their share value and push that into the stakes list. So this is going to be the long Ethereum address, and in the example we were looking at earlier, this is going to be the 100. Once we have our list of stakeholders and our list of stakes, we have to get the current account again. Right now, we're not doing a good job of keeping track of the accounts, so we have to query for them periodically. Most of the time, that's cached by your Web3 provider, and it doesn't have to go anywhere to get that information, so it's a cheap call to make. We start a watcher for the affiliate factory contract affiliate deployed event. So when the sign-up completes, the contract will emit an affiliate deployed event. And we want to look for affiliate deployed events for the sender of this transaction. That gives us an easy way to find the affiliate event or the affiliate deployed event so that we can find the affiliate contract so that we can take you to the right dashboard. With that watcher in place, once that watcher returns a result, we are going to clear the interval, and we'll talk about the interval in a minute. We're going to stop watching on the watcher, and we are going to redirect the user to their dashboard page. That's not right. I need to fix that. It shouldn't be result.args.sender. It should be result.args.address. For the then we call the affiliate factory contract sign up function. We pass in the stakeholders, we pass in the stakes, and we pass in the values. If you remember from last week, these are exactly the arguments to the affiliate contract sign up function that the contract written in Solidity is going to expect. So we're passing in the arguments that it expects, and those are going to be translated from Web3 into what by Web3 into what the contract is expecting. So we're saying that we are sending it from account 0. We have to specify what Ethereum address is paying the gas for this transaction. Then we have our callback function. Once the sign-up function gets submitted, it will return a transaction ID. And this does not mean that the transaction has been confirmed on the blockchain. That might take minutes, hours, or days, depending on how congested the network is and how much the user elected to pay for gas. But right now, we will have a transaction ID. If an error came back, then we are going to pop up an error dialog and tell the user that the error has occurred and show them the error. In the vast majority of cases, this is because the user has rejected the transaction. There are not too many other situations where you would get an error at this phase. At this point, the contract has not tried to execute the transaction. So if there are errors that occur in the execution of the transaction, that is not going to come back in this particular case. So if we got an error, we open the error dialog and show the user the error, so hopefully they can fix it. If we got a valid transaction ID back, then we update our Etherscan link to link the user to that transaction ID, and we open the transaction dialog. Then we set an interval, and once every second, we ask the blockchain whether or not this transaction ID has a transaction receipt ready. Once it has a transaction receipt ready, that means that the transaction has been confirmed. Until that transaction receipt is ready, this will keep iterating and coming back with an error. No, wait. Oh yeah, this is an interval. So I don't know. I think maybe this function doesn't fire until we get a transaction receipt. I don't remember exactly, but this works. So in any case, once we succeed here, we will clear the interval, so it will stop firing. We will stop the watcher that was watching for the event, and we will redirect the user to the dashboard. Note here that the address we are sending them to, we are pulling out of this transaction log, and since we just have a generic transaction receipt, we don't know the nice names of all of the fields. We just have to know exactly where to find everything. And in this case, we get the affiliate contract address from bytes 26 to 66. Any questions about this? Okay. Oh, sorry.
I was just saying.
Okay. So a couple of notes for monitoring for transaction confirmation. There are two ways to monitor that a transaction has been completed. You can watch for transaction receipts, but this has a problem. It is possible that if a user click that Etherscan button and Etherscan says that the expected confirmation time for this transaction is 3 days, they might go, oh God, that's terrible. And MetaMask gives them a nice button that they can go push, and they can resubmit the same transaction with a different amount of gas. It will use the same nonce and the same transaction data, but they can add more gas so that the transaction confirms sooner, and they don't have to wait the 3 days that Etherscan told them it was going to take. The problem with that is that when they resubmit a transaction, it gives them a different transaction ID. And the different transaction ID means that we're watching for the wrong transaction ID, and it's never going to show up as confirmed. MetaMask doesn't give us any way to detect those events that the user has resubmitted the transaction, so we can't always be guaranteed that the transaction completion is going to be confirmed by a transaction receipt for the transaction ID that we were initially made aware of. The other option is to monitor for events. So we are doing both of these. We looked at the first one where we were watching for the affiliate deployed event, and we were watching the second one where we were monitoring for the transaction receipt. Depending on what Web3 provider you have, one of these might be more reliable than the other. The fact that I just realized that I was pulling the wrong piece of information off of the event tells me that the vast majority of the time, when my transactions have completed, we have gotten the transaction receipt before we have gotten the event, and thus we have canceled the watchers in the intervals, and we have never, as I have been testing this, gotten an event back. Generally speaking, I find MetaMask to be not very reliable for event processing. But if you are building a dApp and an event is particularly important, you should do both. In this case, the event is very important because that is the only way we have to find out what the affiliate's address is, or what the affiliate contract address is after the transaction has been confirmed. So, right, basically, the affiliate contract address comes back in the message, and unless you capture that message, you don't know the address of the contract that just got deployed. Once we've confirmed that transaction, the dashboard, or the user gets forwarded to the dashboard. So here we're going to look at the setup for the dashboard dApp. We have the window.web3 object. Once again, we wrap that. And it's just kind of implied that this is within the window.onload function. I haven't shown that wrapper here. Again, these are different pages with different sets of JavaScript and HTML. Again, we have to get the network to make sure that we're interacting with the right address. So we have a tokens to check variable. If we're on network 42, that's Covan, then we're going to watch for 0x and wrapped ether. And we have the images, image links, the addresses, and down here at the end, a divisor so that we can show with the conventional decimal places. If we are on network 1, so that's mainnet, then we have ZRX and WEATH and Embiggen, and these are all the actual mainnet contract addresses for those respective tokens. And even though at the time that I developed the dashboard and put these slides together, we didn't have the affiliate factory ready for sign up, and we didn't have the sign up address on the sign up, or the factory address on the sign up page. All of these tokens already existed, so we were able to embed those here basically as soon as we started development on the dApp. Once again, we have a contract setup phase. Here we are setting up a base token contract. So this is going to be web3.eth.contract, and then the token ABI. Once again, token ABI is very long. In this case, we are instantiating the token base contract without giving it an address that it's associated with. So we have multiple tokens that we're going to need to interact with. We can start with the same token base and then do token base.at contract address and interact with each contract without having to set up, go through the whole ABI stage multiple times. Excuse me. Next, we need to be able to interact with the affiliate contract. So once again, we have the web3.eth.contract, and then we provide the affiliate ABI. In this case, we do know the contract address, and there's only going to be one that we want to interact with. So we pull out of the URL the affiliate contract address, and we set up our affiliate contract address ready to interact with that affiliate contract. And then immediately, the next thing that we do is we call affiliate contract.relayername.call. This is going to make a call to the blockchain to get the relayer name off of this affiliate contract. And it is going to call this callback function when it succeeds. And we are going to update the relayer name elements, and there's more than one of them, with the text from the relayer name. Any questions about the contract setup?
Yeah, so if there was an issue in the monitoring step that you've gone over previously,
yes.
I recall you saying that if that step messes up, you don't have a way to find out what the new contract address is.
Yes.
Wouldn't OpenRelay have a way to find that out from themselves?
Yes. Yeah. So, yeah, I mean, we can go to Etherscan. We can find, or we can go to our own system and we can find the list of all of the addresses that are provided to us. We don't have a great way. The problem with our current setup is we don't have a good way to say, okay, this is one of the addresses that I intended to pay out with this affiliate. And let's look up the affiliate contracts based on the people who are going to get tokens when the payout function gets called, which I think ideally would be the way you would want to go look those things up. You can't do that on chain, and we don't really have a good off-chain index of our affiliates yet. We might at some point in the future. Practically speaking, I don't expect we'll get more than a few affiliate signups on a given day. I would be thrilled if I'm wrong about that, and we got hundreds of affiliate signups every day. So but practically speaking, I think if you can tell us about what time you signed up, we can go get your affiliate address. Or likewise, if you just looked at the transaction receipt on Etherscan, that will give you the contract address, and then we can set you up and get you access to the dashboard. So when I say it's important that we get the affiliate address from the event, it's true from a user experience perspective. If we don't capture it through one of those two ways, the user is going to have a bad time, but it's not like we necessarily have to redeploy the whole contract. Does that answer your question?
Yep. Maybe add that to the page whenever it's getting that in case there's an error. You can follow this process.
Okay. Yeah, that makes sense. All right. So one of the things that the affiliates dashboard has is a table of all of the balances that the user had, that the affiliate contract address had. So here we are going to populate that table. We start out by removing all of the rows from that table and hiding the payout button. So we remove the rows because if there's already rows there, we're about to add new rows, and we don't need to list the same balances or balances for the same token more than once. We hide the payout button. Then we create a list of tokens that would be paid out if the payout button were pressed. Then we iterate over the list of tokens that we care about for this particular network. So if it's Covan, it's going to be ZRX and Wrapped Ether. If it's mainnet, it's going to be ZRX, Wrapped Ether, and Embiggen. For each of those tokens, we are going to inject a row into our table. So we create the row here, we inject it into the table here. We are going to find the icon element, and we are going to set its source attribute equal to the icon for this particular token. We are going to find its symbol element, and we are going to set its content equal to the token name. And then we're going to take the token address, go to the base token contract for that particular address. So now, basically, at this point here, we are getting the balance of the token at that address. We pass in the affiliate contract address that we've pulled out of the URL, and we give it a callback function to call back once Web3 has our answer. So if there was an error, we fill in the balance slot with an error. We don't tell the user what it was or log the error, because what are we going to do? Yeah, we probably ought to log that at least. And then we are going to, if we didn't get an error, we are going to fill in the balance with the balance we got back from the result. Now, this balance that we got back from calling the function is going to be in the base units. So we are going to divide by whatever its divisor is and fill that in. So, if it's Ether and we got, in our earlier example, 0.05, that's going to be 5 times 10 to the 16th. And then by dividing it by the Wrapped Ether's divisor, that's going to end up showing up as 0.05 on the dashboard. If for any given token we have a balance that is greater than 0, we push that token into the payouts list, and we show the payout element. Remember, we hid the payout element up here, or button up here. Down here we show it. If we have multiple tokens that have balances, then we end up making the payout button visible more than once. But since there's only one payout button, you still only get one of it. And so, yeah, as this populate table function executes, the table gets filled in. The balances pop in a few hundred milliseconds after the rest of the table fills out. And then you have a dashboard with all of your balances. Any questions about the balance table? So that's pretty much it for the Web3 interactions dealing with the affiliate signup DApp and the affiliate dashboard. We covered several Web3 interactions. We talked about the Web3 object setup. We talked about the contract interfaces. Oh, we didn't go into much detail about the difference between calls and transactions. I'm going to back up for this one. Here, when we did this base token dot balance of, and then called this is a contract call. Since the balance of function is read only, calling this function does not constitute an on-chain transaction. We just go out to our Ethereum node. It calculates the value based on, by calling the balance of function on that particular contract, gives us back the result, and that's not a transaction that has to go out to the network as a whole. So that is a call. Calls are cheap. You can make them fairly readily. By comparison, if we go back to, I don't have the payout button on here. Oops. Anyway, the payout button is fairly similar to the sign up button. Here we have where we call the affiliate factory contract dot sign up. That is not a call, that is a transaction. And that transaction is going to have to go out to the blockchain. You're going to have to pay Ether for the gas to execute the transaction, and you're going to have to wait for that transaction to get confirmed. So when you can use calls to get the information you want instead of submitting transactions, that's generally easier and way cheaper. The other thing that we noted is in places like this, when we call balance of, the result there, here balance, is going to be a JavaScript big number object. So JavaScript number objects are floating point values and can represent integers precisely up to 2 to the 53rd or 53 bits. Because Ethereum integers are represented as 256-bit integers, JavaScript's numbers are not precise enough to deal with token balances correctly. So there is a big number library that is available on the internet, and it is very, very commonly used within Ethereum-related projects. The Web3 system, when it is giving a dApp a value that comes out of a big number, or out of a 256-bit integer from a contract, it will give it to you as a big number object, and then you can interact with it by doing things like divide or add or toString. So anyway, that's big number objects, and don't make the mistake of thinking that when you get a result back from a Web3 API call that you're going to have a conventional JavaScript integer. You need to interact with it through big number methods instead of symbols like plus and minus and divide. So as I noted, as we started going into this, we're using jQuery and jQuery UI, but the principles that we've just talked about generally apply across frameworks. You still have your Web3 object, you still have your contract interfaces, you still have transaction calls and values, you still have to deal with big numbers instead of JavaScript numbers. There are obviously some things that will vary between JavaScript frameworks, but most of the Web3 interactions that we've just talked about are not among them. Next week, I will round off the 3-part series on the affiliate program by talking about our affiliate monitoring service. I don't think that will take the full hour, so I will probably also have something prepared to talk about OpenRelay's upcoming widget framework that we have started piecing together. That's a piece that I'm really hoping to get a lot of feedback from the community on and get some community involvement on as we start putting together an OpenRelay front end and creating tools that will enable community members to build services that will interact with OpenRelay. So that's it for the Affiliates Program Part 2 presentation. Does anybody have any questions before we go off the air?
None here.
All right. Thank you all for joining. Again, the slides are available at slides.openrelay.xyz. And we'll see you next week.
Thanks.